So I'm going to try and sell you a car here. I'm going to try and talk to you a bit about how do you go about buying a car. What do you look for? Well, you could be looking at pictures like this one, and you could be looking at what the car looks like, what the color options are, you know, if you would be embarrassed to be seen in this kind of car or not. But the problem is that these pictures don't tell you everything. So like for this example here, we don't even know if this car has 4 wheels because we can only see 3. As far as we know, this is just an empty shell. This doesn't even have an engine. We don't know that. But even if we can find those things out, there's a lot of data and a lot of information we might want to know that we just can't learn from physical objects because we just can't perceive them. And so, for example, what mileage does this car have? What kind of power does it have, and so on. And so for this, we have visualization, which looks like this. This is called Peril coordinates. This is a technique that, in this case, is showing you 6 properties for about 350 cars. From left to right, you can see mileage, number of cylinders, horsepower, weight, acceleration, and the year. And what I've picked here, basically on the top, leftmost axis here on the miles per gallon, is I've picked the top car. So I want to get a car with a really good mileage. And you can see that these are cars that all have the same number of cylinders. They've got low horsepowers, low weight, but their acceleration is all over the place. So maybe I want to find a car that has better acceleration than the rest of the field here. And so be looking at that, I can now pick another value here, and I can say, well, this is my car now. This is the one I wanted to see because I've picked it based on data, on properties of this object that I couldn't otherwise have seen. What's interesting here also is that you saw that I picked the top values, the highest value on the mileage axis, whereas on the acceleration, I picked the lowest value. And that is because acceleration is measured in seconds it takes you to go from 0 to 60. And so the fewer seconds I have, the faster the car is, or at least the faster it can accelerate. And this question or this kind of basic idea of up being more mileage or more seconds or more cylinders is something that's very much ingrained in us. And we actually use that a lot in all kinds of visualizations, even much simpler ones than this one, like, for example, in a bar chart. This chart was released by the Obama administration a couple of months ago, and it shows you job losses over about 2 years, and it shows you in red the job losses under Bush, and in blue the ones under Obama. And what you can tell from this is because the bars are pointing down, is that longer bars are bad. This is not what's supposed to be there. You want to get the bars to be shorter. And so the effective way of using this idea of up being better and down being worse, it really works very much here because it doesn't distort the data. It shows you something actually that's very readable. We're very good at reading numbers this way, but it also communicates to you what you're supposed to be looking for, and it gives you an idea of what's good, what's bad. Of course, there's a political message in this as well, but the point of this is that it's showing you data. It's showing you data in an undistorted way and still gets it across. Bar charts are also a part of this next example I'm going to show you. This was work done about 10 years ago by Barbara Tversky and her colleagues at Stanford. They were showing this chart and the second chart to people and asking them, what do you see? Describe what you see. And so what you see here is actually on the y-axis, which is missing, is body height in inches. And so you're saying, well, 12-year-olds in general are taller than 10-year-olds, and men in general are taller than women, right? So nothing very surprising. But then they changed this to be a line chart instead. And now people were saying, well, it looks like for the left one, they were saying, well, as you're getting older, you grow, right? Makes sense. But for the right one, they said, well, it looks like you get taller the more male you become. So people were interpreting what they were seeing, even if it didn't make any sense. And so there's a very strong connection in how metaphors, visual metaphors in this case, or visual structure, works, how we use a visualization or a particular chart, even something very, very simple, 2 data points, bar chart or line chart, the most basic thing you can do, and how that actually gets a particular message across. And so based on this, we did some of our own work and looked into this kind of very simple tree map here that showed that we were telling people, was showing them a company, different divisions here were represented by different rectangles. And each rectangle has just some random color, but the size represents something about it, like the profits or whatever this division makes. And we asked them to tell us something about what they thought about this company. Does this seem like a stable or very rigid company? Does this seem like a good place to work? Is there communication going on between those departments or those divisions or not? And in this case, people said, well, this is very rigid. This is very much set in this way. You can't change anything here. And also, there's not much going on between the departments, which is probably due to the lines between these rectangles, because they're boundaries, they're borders that you can't go through. But in general, people said, well, this is just rigid and kind of set in stone. You can't change anything, and they wouldn't want to work there. And then we showed them something else, which is a kind of a donut chart. And it should be coming up any second now. I can get this to advance. That is this one, right? So this donut chart is the same as a pie chart. It's just got a hole punched out in the middle. And this no longer has the borders. And because it's round, people felt that this was much more lively, much more vibrant, and there are no more boundaries between the different departments. And we also asked people to tell us why they thought that. Why do you think that this is a much more vibrant, much more flexible place? Actually, the interesting thing is men were much more likely to think that round shapes were more controlled, whereas women said the same thing about square or rectangular shapes, which is kind of interesting. But the interesting thing about this one was that somebody said, you know, this looks like it might just roll away. And we were stumped by this. We were like, this is totally abstract. This is just a circle. How can you say that? And then I showed this to Mike Worth, who's an artist, and he said, well, of course. When you look at the right-hand side there are all the darker colors. They're heavier. And on the left hand, you've got yellow, which is much lighter, not just in brightness, but also lighter in what we perceive it to be in terms of weight. And so it's just off-center. It's going to roll away. And this is what it would be doing if you were to look at this. And actually got it to do that. The interesting thing is this only works because there's gravity. There's no motion if there's no gravity. And so we looked at this at some art psychology, Rudolf Arnheim's work on what he calls the power of the center and a lot of the abstract art. This was done by Joseph Albers. It's called Homage to the Square. And you can see that it's centered horizontally, but not vertically. And it wouldn't work if it were vertically centered. It would just look odd. But this case, in this way, it seems calm, and it just makes sense the way it is, because gravity was able to pull down these squares. Same thing happens in topography. The lower part of this is actually heavier and wider and larger than the top. If you don't see it, you should see it now. And that gives it much more stability. It doesn't look like it's going to move around. It gives it a certain calmness and makes it easier for us to perceive it as not being something that's going to weirdly move around by itself. We did some more work, and I can only just very briefly mention this, on how we perceive data being changed by gravity. So this is a simple bubble chart, and the bubbles that we were pointing at there was the arrows, are the ones that we asked people to pinpoint after we had removed them. And people actually saw them as being further down than they actually are, consistently. And when there was a cluster of objects somewhere, a cluster of bubbles, they saw that one that we pointed out and removed actually as being closer to that cluster. So there's gravity that's pulling down, and there's also gravity that's pulling towards a center, and it's pulling towards other objects. So what I'm trying to tell you here is that visualization is a way of looking at parts of reality that we just cannot directly experience and directly see. And a lot of people think or like to say that, and this was also mentioned in the introduction, that visualization is art, or that there's art in visualization. But I think this is an insult to artists. We've seen a lot of great art this morning, and this is not the same thing. What this is, or what it should be, is a science. And what I'm trying to do, and what others are trying to do now, is to build the foundations of the science of visualization, where we understand how we look at things, how we perceive visual shapes, how we attach meaning to those shapes, and how those shapes are, and our perception of them and our cognition of them is based on evolutionary processes, our experiences in the physical world, and how those impact what we can see in a visualization. And not just for buying a car, but for all kinds of data, of course. Thank you.